whenever we have a first order system, if we give a step input, we are likely to get exponential response, isn't it? We are likely to get exponential response. Even if we are having, let's say, impulse input, then also we will get exponential response. But let's say if we are having a sinusoidal input, then at steady state we are likely to get a sustained sine wave. Okay, we will prove that. And there is one more input which is usually considered, that is the ramp input. So if you are giving a ramp input is the unbounded input, isn't it? So in that case, your output will also be unbounded, isn't it? But for all bounded inputs, your response is bounded. In case of first order process, you will see that first order processes are always stable. Okay, we will come back to this particular point when we will see the stability of the control system. First order systems are always stable. First order system are stable, second order system are stable. System starts becoming unstable when we move from second order onward. Or if the system is associated with time, then even the first order system can become unstable. Okay. All these facts we are going to look at little bit in more detail as we go ahead. Okay. Alright. Okay. So in the last class we started with the discussion that whenever the model equation is a first order differential equation, we are likely to get a first order system which is characterized by a transfer function which is nothing but Kp divided by tau ps plus 1, where Kp is the process gain and tau p is the time constant of the process, isn't it? So same thing we have derived here. You can see this is the first order differential equation. I can rearrange this equation. So after rearranging, what we get is tau p dyt by dt plus yt equals to Kp f of t, isn't it? I can subtract a steady state equation from this and I can get the equation in a deviation form, and if I apply the Laplace transform, I am likely to get this equation Kp divided by tau ps plus 1. So transfer function g of s, which is nothing but what? Which is nothing but output in a deviation form divided by input in a deviation form, is given as Kp divided by tau ps plus 1, where Kp and tau p, these are the characteristic parameters of first order process. Okay, this is what we have seen in the last class. Same discussion which I was saying is given here, isn't it? First order process physically you get whenever there is a capacity to store mass, energy and momentum, and there is a resistance to flow of these quantities, then you are likely to get a first order system. So actually a system is a buffer between inflow and outflow, where there is a capacity to store mass, energy and there is a resistance. Okay. Typically, if you look at most of the process systems are first order systems. You can take the example of tank. You can take one tray in a distillation column, you can take pump, all these, even CSCR, all these systems are first order systems. Okay, correct? So this example again we have seen, we said that there is a tank is there and there is a inlet feed rate is there Fi, outlet is F0, there is a resistance to flow which is R. For a simplicity, we have assumed that the outlet flow rate is directly proportional to the hydrostatic head present here, isn't it? So clearly the outlet flow rate F0 is given as H by R, and if we write down the model equation in this case, the model equation in this case is A dH by dt is given as Fi minus F0, isn't it? And F0 I can replace by H by R. Isn't it? That's what we have done. F0 we have replaced by H by R. And this equation again we can rearrange. After rearranging, what we get is AR dH by dt plus H equals to R Fi. Isn't it? We can write down this equation at a steady state. So at steady state this is going to become 0, H is going to become Hs, and the right hand side is going to become R Fis. If I subtract this steady state equation from the original dynamic equation, we will get an equation in a deviation form like this. In this equation, AR we are representing as time constant, whereas this R we are representing as KT. Okay. This is very important thing. Very often people ask in the interview, what is the time constant for the tank? Time constant for the tank is area of the cross section multiplied by the resistance to flow is nothing but the time constant of the tank. Again, people ask the question that what will be the steady state, what will be the process gain for a tank system? Process gain for a tank system is just resistance R. Okay, alright. So once we have obtained this equation, I can take a Laplace transform of both the sides, and if I rearrange, what I am going to get is that transfer function which is g of s given as h dash s divided by f I dash s, which is given as kp divided by tau ps plus 1. So you can see that this equation you are going to get again and again whenever you are having a first order process. Correct? So this we have already seen. Correct? Then after that we have extended our discussion to a pure capacitive process. We said a pure capacitive process is that process in which there is a capacity to store the mass, but there is no resistance. There is no resistance, and that is why we are naming it as a pure capacitive process. There is no resistance here, and that's what is happening here. You can see the outlet flow rate is not dependent on the hydrostatic head here. The outlet is fixed, because outlet is directly coming from the pump, isn't it? So if you write down the balance equation in this case, it becomes A ds by dt Fi minus F0, and F0 is constant only. It's not changing. It's not dependent on the height, isn't it? So you can see that we can rearrange this equation. So what we get is ds by dt is Fi minus F0 by A, and at steady state it becomes Fi minus F0 by A. If we subtract this steady state equation from this original dynamic equation, we get an equation in a deviation form, which is ds dash by dt, which is given as Fi dash by A. And if you rearrange the term, and take the Laplace transform, what you get is h dash s divided by Fi dash s, that comes out to be 1 by as. So unlike the equation which we get for a first order process, which is Kp divided by tau ps plus 1, in a pure capacitive process we get a transfer function which is Kp dash by s. That is what we have defined earlier. Kp dash by s. This is the equation which we get for a pure capacitive process. So once we get this, let's take a simple case here. Let's assume that the inlet is a step input of magnitude unit here. So that means Fi dash s, which is the input in this case, is a step input of magnitude unity. So what will be the Laplace transform? Laplace transform will be 1 by s, isn't it? I can multiply this Fis here in this equation. What we are going to get? H dash s is given as Kp dash divided by s square, because Fi dash s is nothing but 1 by s. So that will become Kp dash by s square. And if I invert that into a time domain, I can get this h dash in a time domain. H dash t is given as Kpt. So what it means? It means that in this particular tank, if there is a small deviation in this Fi from its steady state value, in that case what will happen? The height of the tank will continuously increase till it becomes overflow. And when this Fi dash is slightly lower than the steady state value Fis, in that case what will happen? This tank is going to get dry, isn't it? It's going to become empty, and that is what is shown here. You can see h dash t will continuously increase or decrease to 0. So you can see that in this case the response is unstable. Response is unstable because the response is becoming unbounded. So pure capacitive process inherently is, in this case, is unstable if you are having a step input. Correct? Is it clear to everyone? Okay. Let's take another case. So in this case, again we are looking at the same stir tank heater system, but unlike the previous case, there is no input coming in, there is no outlet going out, isn't it? The reaction mixture is getting heated by the heat supplied from this heating jacket here, heating coil. Okay. So you can write down the balance equation in this case. So there is only one equation possible in this case. No reaction is occurring, no inlet feed is there. So only equation we will have will be energy balance. What will be the energy balance in this case? V rho Cp dt by dt is given as whatever the amount of heat added here. There is no inlet heat, there is no outlet heat, isn't it? There is no feed in, feed out, correct? So the only terms which are going to have, which will be there, will be Q. So V rho Cp dt by dt is given as Q, and Q is nothing but what? UAT T minus TST. In this case, the heat is supplied, so it becomes UAT TST minus T. Correct? Now this equation, again I can write down this equation at steady state. So at steady state, this left hand side is going to become 0, right hand side will be UAT TSTS minus TS. That's what we are saying. And I can subtract this steady state equation from this original equation. If I do that, we will get this equation in a deviation form, which is nothing but V rho Cp dt dash by dt, and that is equals to UAT TSP dash minus TS dash. Sorry, TSP dash minus T dash. Okay. I can divide this entire equation by UAT, so V rho Cp by UAT, and I can define that as time constant, tau p. So in that case, what I am going to get? Tau p dt by dt, and this T dash I can take it on the left hand side, that becomes tau p dt by dt plus T dash, and that should be equals to UAT into TST, isn't it? Sorry, it will be just TST. So that one which is there, that I can represent as Kp. So I can represent this entire equation in the same way we have generalized our first order process, isn't it? So in this case, the transfer function we will get will be Kp divided by tau ps plus 1, where Kp is just 1, whereas tau p is V rho Cp by UAT. That will be the tau p, isn't it? Again, you can go back to the definition of the time constant. See here, tau p is defined as V rho Cp by UAT. In this case, V rho Cp is nothing but what? Capacitors to store the energy, thermal energy. Whereas 1 by UAT is nothing but the resistance to the flow of energy. Isn't it? So it is nothing but the multiplication of capacitance into resistance for flow of energy. Correct? So same physical significance of the time constant which we have studied earlier is retained here also. Okay. And Kp is just 1. Is it clear to everyone? Hello? Yes, no? Okay. Now let's look at the solution of this particular equation. So equation given here is Gs is given as Kp divided by tau ps plus 1. Let's assume that the inlet in this case is a step input. So step input of magnitude UDT. So in that case, if you find out the Laplace transform of input, what we are going to get? We are going to get 1 by s, isn't it? So this f of s is nothing but what? 1 by s. I can multiply this f of s on the right hand side, and that will give me ys, isn't it? So ys will be given as Kp divided by tau ps plus 1 into f of s, whereas f of s is 1 by s for unit step input, isn't it? So we are going to get 1 by s into Kp divided by tau ps plus 1. Now, whenever we have a polynomial like this, what we do? We find out the roots of the denominator, and based on the roots, then we separate the partial bracket. That is what we do. So same thing we are doing here. So here the first root is at s equals to 0. So that will be C1 divided by s, isn't it? Plus this, in this case the root will be what? Minus 1 by tau p. So I can divide this second root by tau p. So we will have, in this case, if I divide this tau p, we will have actually Kp divided by s plus 1 by tau p. That is what we are going to get. So root will be at minus 1 by tau. Correct? So here both these roots are located where? Where they are located? The first root is at s equals to 0. So this root is located at origin. Isn't it? The second root is minus 1 by tau p. Tau p is a time constant. Time constant cannot be negative. It is always positive. Isn't it? That means minus 1 by tau p is a root which is located on the left hand side of the imaginary axis. It is having a negative real part. Isn't it? So that means both the roots are real and distinct, and they are located on the left hand side of the imaginary axis or on the origin. So what response we are expected to get? Stable response we are expected to get. And since the roots are real and distinct, the response is going to be exponential. Remember, when the roots are imaginary, in that case we get periodic response. In this case, the roots are real and distinct, and they are located on the left hand side of the imaginary axis. We are likely to get a stable response with exponential behavior. Correct? So if we invert back this particular equation in a time domain, what we are going to get is yt comes out to be kp 1 minus e raised to the power minus t by tau. This is what the equation we are expected to get. Now this is for a step input. Let's say instead of having a step input of magnitude unity, let's say we have a step input of magnitude a. In that case, what we are likely to get? We are likely to get a kp 1 minus e raised to the power minus t by tau. So this is the solution of the first order process. This is the solution of the first order process for a step input of magnitude a. Correct? Isn't it? Step input of magnitude a. Now this particular equation is very important. Why? Because we can find out the physical significance of kp, tau p, and we can get more information for the first order response based on this equation. Okay. And for that, what we have done here is we are plotting yt by a kp versus t by tau. So yt by a kp we are plotting with respect to t by tau. So in a way, what we are doing? In a way, we are plotting our output response y with respect to time t. Remember, in this case, a, kp, and tau p are the constants. So actually, we are plotting output yt with respect to time t. My response will look like this. It will go from 0 to 1. It will go from 0 to 1. So response is exponential like this. Okay, correct. So what it means, at time t equals to 0, my system was actually at a steady state. And once I have given a step input of magnitude a, in that case, my output increased, but finally it also reached to a steady state value. And it became constant. It is not becoming unbounded. See, this response is not unbounded, it is becoming constant to a value 1. So system response is stable. The only thing which is happening here is I am moving from initial steady state to the another steady state. That's it. Over the period t tends to increase. Correct? Do you all agree with me? Now this particular graph is very interesting. Very interesting in the sense that, remember what is the x-axis here? X-axis is t by tau. So where I am representing this 1, what it means? Time is equal to tau. That means time is equal to 1 time constant. When I am taking 2, it means that time is equal to 2 time constants. When I am taking 3, it becomes time is equal to 3 time constants. Now the interesting fact here is, in a first order response, if you follow the initial rate of increase, then the entire response completes in 1 time constant. Can you see? If I continue with the same slope which is there at time t equals to 0, in that case this entire response is going to complete in a 1 time constant. So that also gives me a physical significance of time constant. Lower is the value of time constant tau p, steeper will be the slope here. Isn't it? Correct. So and the faster will be the response. So you can see that the systems which are having the low value of time constant, their response is faster. And the time constant is higher, that means what? The system response is sluggish. So in this case, the speed of response is actually obtained from this tau t. And that is why this constant we are calling it as a time constant. Okay. Now you are able to correlate why we are calling it as a time constant, because it gives you a speed of response. Lower is the value of time constant, faster is the response. Higher is the value of time constant, sluggish is the response. Okay, is it clear to everyone? Another interesting fact here is, if you find out what will be the response at time constant 1, what will be the response when t is equal to tau p? When the time is equal to 1 time constant, what will be the response? I can find out that directly here. If I put this t by tau t equals to 1, e raised to the power minus 1, and if I rearrange everything, what you are going to get is this particular value of yt by akp, that comes out to be 63.2%. Okay, that is also another way of finding the time constant. Remember, in this case, time constant tau p and kp, these are the constants which you have to find out by performing the experiment, isn't it? These are not given to you. These are not given to you. What you have to do is, you are having, let's say, experimental setup. You have to give an initial step input, and based on that you are going to measure your output, and then you are going to draw this curve based on the data you are getting. And once you get this data, from this data you can find out what is the value of kp, what is the value of tau p. All these constants you can find out from the data. Yes, clear or not clear? Let's say you are having a tank. Let's say you are having this tank. Not this tank. This tank is given to you. Okay. And your boss asked you to find out, the time constant of the process and the process gain experimentally. Why experimentally? Because unless you have this value, you will not be able to put it in the equation, isn't it? And then you will not be able to control it. You know a priori that this is a tank system which is going to be the first order system. That you know a priori. Okay. Now what you have to do? Manually you can increase this Fi value from whatever the steady state value you are having by, let's say, magnitude of 1. You can increase this Fi value with the magnitude of 1. So initially it was Fis, the new value is Fis plus 1. So that means Fi dash is equal to 1. Isn't it? Once you give a step input in Fi, then you measure the height of the liquid in the tank with respect to time. Initially nothing will happen. As you have increased, you will start from the value of 0, h dash value will be starting from 0. Isn't it? As time goes, this h dash will increase and it will settle to a new value. And then you are going to get the same graph. The same graph you are going to get. Correct? Once you have obtained this graph, then you can find out the time constant directly by finding this. See, once you have obtained this graph and this final value at sufficiently large time also you have found out, isn't it? And 63.2% of this final value will be somewhere here, and this particular time will be corresponding to the time constant. So you can experimentally find out the time constant. Similarly, you can find out Kp also. Kp is what? Kp is nothing but change in the output divided by change in the input. In this case, the change in the input is 8, and change in the output is whatever the value you are getting here, isn't it? From 0 to 1, isn't it? 1, correct? And if you divide this, you are going to get Kp value. Correct? So you can find out Kp and tau p directly by performing the experiment. This was one of the questions I have given way back. Okay. So clearly this is not going to come this time, isn't it? Question was how you will be finding Kp and tau p experimentally. That is what the question given. Okay. Okay, so the same discussion is written here. A first order lag process is self-regulatory. Why we are calling it as self-regulatory? Anyone tell me? So if there is a disturbance coming in, because of disturbance, your output is going to change. But at t tends to infinity, your output is going to stabilize to a new steady state value. So it is self-regulatory. It's not becoming unstable. Okay, is it clear to everyone? Then, for a tank system, inlet flow increases, liquid level goes up, hydrostatic pressure goes up, flow out increases, and finally system stabilizes to the equilibrium state. That is what is given. Again, in this equation, yt by a kp is given as 1 minus e raised to the power minus v by tau p. You can find out the slope of this curve at time t equals to 0. How you can find out? You can differentiate this equation with respect to p by tau, and then find out what is the value at t equals to 0. So if you do that, that comes out to be 1. So that is what is obtained. See, the slope of this curve is just 1. See, this value is 1, this value is 1. Correct? So you can find out the slope at time t equals to 0. So from this you can conclude that if the initial rate of the response is continued, in that case the response will be complete in 1 time. Okay. Then the next conclusion is the smaller the value of tau p, steeper the initial response of the system, and faster will be the response, isn't it? So tau p in a way gives what? It is nothing but the time necessary for the process to adjust to a change in its input. Okay, so the initial slope is maintained. Correct? This table is very important and very often asked in the interview also. So in one time constant, the response reaches to 63.2% of the ultimate response. In 2 time constant, it reaches to 86.5%. And in 3 time constant, it is 95. In 4 time constant, it is around 98% of the final response it reaches. Okay? Correct? Okay. Now this slide is also interesting in the sense. Okay. So remember, we have found out what is time constant. But there is another constant which is Kp, which we call it as a process gain. So Kp is defined by what? Kp is nothing but what? Change in the output divided by change in the input, that gives you a Kp. And this, so at steady state for an input magnitude of A, when t tends to infinity, my output yt is a Kp. So if I divide this a Kp by A, we get Kp. Isn't it? Correct. So what it means? The change in the output divided by change in the input, that will give you directly the Kp value. Directly the Kp value you can get. Okay. Now, considering these 2 parameters, let's look at 2 different cases here. And these two cases are very important, because you will see, if you look at last 25 years GATE paper, you will find at least 2-3 questions on this. Okay. Now the 2 cases here are, there is a large tank system. Here this tank is larger. So when I am saying this tank is large, what I am saying is this cross-sectional area A is large. Then there is another tank system where the area A2 is small. Okay. We are considering 2 cases. One case is in which this resistance R and this resistance R both are, let's say, same. That is case number 1. Another case is if this A1 is large and A2 is small, but we are taking this R in such a way that their time constant is same in both the cases. So time constant is same means what? Remember, A into R is the time constant. So proportionately the R is also decreasing here, and proportionately R is increasing here, so that A1R and A2R both become same. So there are 2 cases. Case number 1 where the resistance to flow is same, and case number 2 in which time constant is same. In both the cases, what type of response we are expected to get? We are expected to get a different response in both the cases. Okay. So let's look at the first case. First case where area of the cross section A1 is greater than A2, and since this R is same, A1 into R is nothing but tau P1 and A2 into R is nothing but tau P2. So clearly, since R is same and since A1 is greater than A2, we can conclude that tau P1 is greater than tau P2. Yes or no? Yes, no. पीछे भाई समझ में आ रहा है नहीं आ रहा है कि सब बाहर जा रहा है? बाहर जा रहा है. ठीक है. There is no effort to slay a ball. है ना जाने दो. So in the first case, the time constant tau P1 is greater than tau P2, isn't it? Tau P1 is greater than tau P2, and remember what we said. What is the physical significance of time constant? It gives you a speed of response, and since time constant tau P1 is greater than tau P2, my first system is going to be sluggish compared to the second, isn't it? When time constant is low, higher is the speed of response, and since tau P1 is greater than tau P2, that means tau P1 is lower. So for tau P1, tau P2 is lower. So for tau P2, we will have a faster response, isn't it? So if I plot the response curve for both the cases when there is a step input, I will get a response like this. You can see in this case, this red curve is for this tau P2, whereas this blue curve is for tau P1, isn't it? Correct. The important point to note down is both these curves are going to approach to the same steady state value. Why? Because ultimate value will be what? Ultimate value will be Kp, and Kp is nothing but what? R1 or R2, both are same in this case. So both these responses are going to approach to the same value. That's why both these curves are approaching to the same value. The interesting fact is this. Now let's look at the second case. In the second case, when time constant is same, time constant is same means what? Time constant is same means what? Their response will be same. Their speed of response will be same. So you can see that both these curves are starting with the same slope. They are starting with the same slope. But in this case, and they are reaching to the ultimate response also in the same time. But their ultimate response will be different. Why? Because in this case, you can see that since tau P1 and tau P2 both are same, in this case you can see that R1 should be lower than R2. So you can see that this R1 is reaching to a lower value, whereas R2 is reaching to a higher value. So their ultimate values are not same. Their ultimate values are not same. They are different. Is it clear to everyone? Correct? Yes, no? Okay. So remember, so far we were only looking at a very simple case where we were assuming that the outlet flow rate is proportional to the hydrostatic head present in the tank, isn't it? We said that this particular assumption is not correct, but we will start with this assumption primarily because this will give me a simple system to look at in the starting, isn't it? The real picture here is the outlet flow rate will be proportional to the under root of H. That is what you are likely to get from fluid mechanics, isn't it? So in this case, the same thing we are doing. We are assuming that the outlet flow rate is proportional to the under root of H. That is what you are going to get from fluid mechanics. Okay. But when we are saying that the outlet flow rate F0 is proportional to under root of H, we are likely to get a non-linear equation because under root is a non-linear term, isn't it? And what is the definition of transfer function? Definition of the transfer function is Laplace transform of output in a deviation form divided by Laplace transform of input in a deviation form. But these two things we have to do it after linearization. After linearization. So in this case, this particular equation, if I write down the equation for this particular case, what I am going to get? I am going to get A dH by dt is given as Fi minus F naught, where F naught is nothing but beta into under root of h. Because of this under root h term, I am going to have a non-linear equation. So in order to find out the transfer function, what I need to do? I need to linearize this particular term. So how we can linearize this term? By applying the Taylor series expansion, isn't it? So Taylor series expansion of this term will be given by what? Beta under root h will be given as beta under root hs, where hs is the steady state value, isn't it? Plus d by dh of beta under root hs into h minus hs. So this derivative comes out to be beta divided by 2 under root hs into h minus hs, isn't it? This entire term is a linear term. Why? Because this under root hs is a steady state value, so you are going to get a constant term here. Here also you are going to get a constant term, and you can see that this entire equation is linear. Okay. So you can put this particular equation in terms of beta under root h and then try to solve this. So in this case, what you are going to get? A dh by dt plus beta under root h will be given as Fi. This beta under root h will be represented by beta under root hs plus beta divided by 2 under root hs into h minus hs, isn't it? And that should be equal to F. Okay. Further rearranging the term means you can multiply this entire equation by 2 under root hs by beta. So with that what you will have? Again, okay, so you can do that, but before that let's obtain this entire equation in a deviation form. How you can obtain? You can write this equation at a steady state. So at steady state, this first term is going to become 0. This term is going to become beta under root hs, because that's a steady state value. It's not going to change. This term is going to become 0. Why? Because h will be equal to hs at steady state. So this term is going to become 0. And Fi is going to become Fis. If I subtract that from the original equation, this beta under root hs term will get cancelled out, and this Fi will become Fi dash s. Isn't it? So that's what we are getting. This Fi dash we are getting here, and the only term left will be beta divided by 2 under root hs. Now I can rearrange this entire term. So we can write down this equation as 2a under root hs by beta dh dash by dt plus h dash equals to 2 under root hs by beta Fi dash. And this entire equation I can represent in a generalized form. Generalized form is what? Tau p dy by dt plus y equals to kp Fi. Isn't it? That is what the generalized equation. I can write down this entire equation in a generalized form like this. Here time constant tau p comes out to be what? 2a under root hs by beta, and kp comes out to be 2 under root hs by beta. Now if you compare this case with the earlier case where we have assumed that the outlet flow rate is proportional to hydrostatic head, time constant there defined was A into R, isn't it? And kp divided by kp is given as just R. Unlike that, in this case, time constant tau p comes out to be what? 2a under root hs by beta. Now this particular time constant value at kp has some meaning. It is not unlike the previous case where it was capacitance multiplied by, here also it is capacitance multiplied by resistors, but it is also giving some more information. And what that information is? This hs value, it is dependent on hs. Hs is a steady state value. And this hs value depends on what initial value of Fi you are doing. So every time you are performing your experiment, your hs value is going to be different. It's not going to be the same. So what it means? Your kp and time constant will not remain constant. They are going to vary from experiment to experiment. They are not fixed. So such systems are referred as non-stationary. Another example for similar type of thing is, let's say time constant we have defined in case of In case of this system, time constant is defined by what? V rho Cp by UAT. V rho Cp by UAT. What is U here? U is a overall heat transfer coefficient. And this overall heat transfer coefficient is going to change as there is a fouling, there is a scaling, there is a corrosion taking place in the tank. Because of that, this U is going to change all the time. So your system time constant is not going to remain fixed. It is going to change with respect to time. Isn't it? Remember, all this entire analysis we are doing with the assumption that Kp and tau p is fixed. And this Kp and tau p are not at all fixed. They are varying. So most of the chemical engineering processes you will see, they are non-linear and non-stationary. In such cases, Kp and tau p are likely to vary. How to deal with such system? There is a challenge. Isn't it? It's not safe. Correct? So in such cases, what we do? In such cases, what we do is either we take the relation how the time constant and Kp is going to change with respect to time. If that relation is known, we can embed in the equation and then we can solve the entire equation in a time domain. So it is going to become more complicated. Another assumption is you can assume for a particular time period Kp and tau p constant, and then periodically you can change the value of Kp and tau. And that gives rise to another interesting adaptation which is called as adaptive process control. Adaptive process control, I am not sure whether we will be able to do it, but there is something called as adaptive process control where you find out Kp and tau p every time you perform the control action. There is an automatic procedure to find out that. Okay. And that becomes that topic is a part of advanced process control. I am not sure whether we will be able to do it. If we get the time, we will cover. Otherwise, the take home message here is in adaptive process control we find out Kp, tau p every time we perform the control, and that we do automatically. Okay. Is it clear to everyone? So this is the last slide which we will cover today. So far we were only looking at step input, isn't it? What type of response we are likely to get when we are performing, let's say, the output in the presence of impulse input. So remember, in this case the transfer function is given by what? Kp divided by tau ps plus 1, and that is given as y dash s by f dash s. Let's say we are having the impulse input. In this equation, what is the input? Input is f, isn't it? F of s. Impulse input, for a impulse, what will be the Laplace transform of impulse? Just 1. Remember, the Laplace transform Dirac delta function is 1. So f of s will be 1. So if I multiply this f of s here, y dash s will be just Kp divided by tau ps plus 1. And if I invert back into a time domain, what we are likely to get? We are likely to get Kp divided by tau p e raised to the power minus t by tau p. And if I plot tau p yt by Kp versus t by tau p, you will get exponential decrease like this. And the same, remember the same conclusion when we have drawn for these step inputs, all those conclusions are valid here also. You can see, if you maintain the initial flow, then the entire response is going to come in one time. Again, if you take 63.2% of the response here, that will be the actual response when t equals to 1000. Isn't it? And when you are having almost 4 time constant, your response will be around 98. Okay. So same conclusion we can derive even in this case. All these studies, all these examples are very easy, but unless and until you do yourself, you will not get it. You will not get it. Okay. These look very, very simple here. They are not simple. A lot of small hidden things are there, which unless you yourself derive, you will not be able to get it. So please, see, everything is available, book is available, notes is available, exams are open book, but don't be the wrong impression that without studying you will be able to do it. That is not the case. I request all the students, please go through, okay? And we stop here, we will continue now. Ravindra is not there, na? Aryan Tyagi, Prathamdeep, Tuhin Kumar Raut, Tanya Gupta, Ayush Amit Agrawal, Kartikeya Nigam, Sakshi Patel, Borde Shraddha, Anmol Goyal, Siddhant Jain, Sparsh Vyas,